Hey everyone, I just wanted to do a quick little screencast about contact forces. In particular, I'm going to be talking to you about the compression force. I'm just going to mention that there are two kinds. There's this compression force or normal force. These all arise out of the ball and spring model. And how they arise out of the ball and spring model is well described in the reading, I believe. So we have the normal force, which I will usually denote with some sort of normal force like that. It's a vector, so I should put a vector symbol over it. And then there's also a frictional force. And there's actually two kinds of frictional forces, a static frictional force and a kinetic frictional force. And I'll just write these down. Like so. Static friction, kinetic friction, and these two forces have a specific form. Kinetic friction has a coefficient of kinetic friction times the magnitude of this is equal to this times the magnitude of the normal force. And I can write down a similar relationship for static friction with one difference, and that is that I use this less than or equal to sign. And so I want to ask, and hopefully we answer in this screencast, the question: why is the less than or equal to sign important? And we're going to answer that question by considering two cases. We're going to talk about what happens, motion on a ramp with low slope, and motion on a ramp with high slope. So you can just imagine that we'll have a ramp with low slope and we'll have a ramp with high slope, and we'll be looking at this angle here to describe each of those ramps. So looking at the low slope ramp, if we think about this scenario, we're going to have three forces. We're definitely going to have gravity. I don't want that there like that. Let's just draw it like this. We're going to have gravity, which is the mass of the object times g. We're going to have the normal force, and this will be of the ramp on the block. And we're also going to have a static frictional force. That the ramp is exerting on the block. So these are all forces that this is the gravitational force, if you will, of the Earth on the block. So all of these forces are on the block, as you can see, and that's why these are all the forces that we are considering on our block here. So part of the issue then becomes this. Let's just think about this for a second. What happens if this theta is equal to 0? Just as a, what do you think? Well, if this is equal to 0, we would expect the normal force and the gravitational force to be opposite each other, right? Because the normal force is always perpendicular to the surface, and in that case the surface would be horizontal. The surface would be horizontal, so we could imagine it'd be like our block was drawn over here. If we have a block over here, we just have gravity, we have the normal force, and if there's nothing moving, we don't if it's not moving at all, we're not worried about friction going either way. There's two forces, they're pointed in the opposite direction, they're going to have to cancel each other out. But, so in this case, the force of static friction would equal 0 here. Now let's figure out what it'll equal when we're not considering this angle to be 0. So if we have a ramp, an angle, and I'm going to make a teeny tiny block up here. We've got the gravitational force. We've got the normal force. And this is perpendicular to that line. And we're going to have the frictional force. I haven't drawn this very perpendicular. Let's consider the y direction to be perpendicular to the surface here, and the x direction to be parallel to the surface here. So all of the forces in the y direction, the forces are going to be the normal force, and we will also have this component of the gravitational force. And if you do a little bit of geometry, this angle here is the same angle as that angle there. Since the normal force is in the positive direction, we can write this y component to be mg cosine theta, and we're going to do a minus sign. And this, because the block is not going to be sliding down the plane, we expect that the momentum is not changing at all in the y direction. We can also do the same thing in the x direction. And we'll write this equation down. And because we know the mass, we know gravity, and we know that we're at some small angle theta, if we want to, we can solve directly for the force of static friction here by just solving this equation. So for low slope, we're going to get that the force of static friction that the ramp is exerting on the block is equal to the mass of the block times g times sine theta. So this is our low slope result. In the high slope case, we're going to be able to write down the so we're going to have two differences. With the high slope case, what is going to happen is this will begin to slip. So if we use the same coordinate system as before, x and y, along the ramp and perpendicular to the ramp, if we do this, one of the things we're going to find is that the change in momentum in the x direction will not be 0. Or put another way, the acceleration in the x direction is not going to be 0. So we can't find the static friction force like we did before. But here we can use the rule, we can say, so this expression, the static friction, this is the maximum possible static friction if it is equal to mu sub s times the normal force. And so we can use this to find that equation. So just like we had, since we had written down before, the normal force is just equal to mg cosine theta, we can write down that we can take this, we can plug it in here, and we can then write, let's see if this works. We can then write that the force of static friction that the block is exerting on the ramp, well, that's also true, that the ramp is exerting on the block is equal to mu sub s mg cosine theta. So this is our other result. So that brings me to how we can measure the coefficient of, this should be static friction. How we can measure the coefficient of static friction. And that is that it's the critical angle where the frictional force that you get where you consider low slope friction is equal to the frictional force you get with high slope friction. So we can set these two equations equal to each other. We can then say, all right, mg cancels out, and mu sub s, so this is true for some special critical angle. Mu sub s is then just sine theta critical over cosine of theta critical, which is the same as tangent. So what you can do if you want to find the coefficient of friction between two objects, you can set up a ramp. Just hold it. You got a table, you got the material 1, you got your block material 2, and then grab one side and lift it up and watch this block, and the instant it starts sliding, you've hit your critical angle. All right, have a good day. We'll see you in class.